Welcome to this HSC physics demonstration for the unit motors and generators. This demonstration will examine the differences between a 2-pole and a 3-pole electric motor. I've constructed for this demonstration an actual 3-pole electric motor using entirely materials from a scrap box. This motor has an armature running on a steel wire as a spindle. The armature body is manufactured from a piece of wooden broom handle. The commutator is a piece of wood as the core with a piece of copper water pipe cemented around the outside of that and then split into 3 segments. The poles of the armature were constructed from 3 steel cup-head bolts, and around each one there is 100 turns of insulated copper magnet wire, about 0.48 millimeters diameter, 100 turns on each pole. The field magnets are originally from old loudspeakers. They are cast alloy called alnico, which is a nickel cobalt aluminium alloy. They're not particularly powerful magnets, but they're quite useful for this demonstration. I've coated the north poles black and the south poles as red on these magnets. So for the motor demonstration I need to have a south pole and a north pole facing towards the armature. It doesn't matter which way they face, so long as they're of different polarity, and we'll look at that later. The brushes I manufactured from pieces of braided copper wire, and they just bear lightly against the commutator segments. So there we go, there's our brushes making contact with the commutator. So in operation this motor is actually quite efficient. It will run from 3 volts DC. I can supply 3 volts using a couple of torch cells. In series, each one of these torch cells is 1.5 volts, so 2 of them together will supply 3 volts potential difference, and we should be able to get our motor to turn with that. Yes, there it goes. Turns anti-clockwise. Now you can reverse the direction of rotation of the motor in 2 ways. One way is by reversing the direction of the current. So we can change the direction of the electric current and the motor will turn clockwise. Another way to change the direction of rotation of the motor is by reversing the direction of the field magnets. So I take these magnets out and turn them around so that north is on the left and south is on the right, and without changing the direction of the current flow, the motor will now turn anti-clockwise. So there's 2 ways of changing the direction of rotation of the motor. Now, the theory of operation of the 3-pole motor needs a bit of explaining. The principal problem of the 2-pole electric motor is that when you have your field at, say, horizontal this way, and the direction of the poles of the motor vertically this way, there's a dead zone on the armature, where the armature experiences no net force and no torque is developed in the motor. This can be a real problem because it means that during rotation the armature is not developing a uniform torque. It's quite, you could say, periodical, the torque characteristic, and there's a point where the motor won't start reliably because there's no net force developed on the armature windings. At a certain position there will be no net force. So it makes it unreliable starting. The 3-pole motor gets around this problem because with 3 poles spaced 120 degrees apart, there will always be one pole which will be close towards the direction of the field magnet, and so there will always be a pole which is attracted towards the field magnet and will kick the motor off and begin it turning. So they can be quite unreliable, the 2-pole motor, but the 3-pole motor is very reliable at starting, and in fact any odd number of poles, whether it be 3, 5, 7 or whatever, is a good choice for designing a motor that's reliable at starting. So this motor should actually be able to run quite reliably from 1.5 volts DC. Let's see if we can get it to turn with 1.5 volts DC. Yes, we can. It turns anti-clockwise. If I reverse the direction of current flow, it should turn clockwise. And it starts quite reliably, even with a very small amount of torque that's developed with a 1.5 volt battery. Obviously with 3 volts DC, the motor will develop considerably more torque, and I'd like to know exactly how much power is being consumed by the motor. Power can be calculated from the potential difference across the armature multiplied by the current flow, so V times I. I can estimate V from the open circuit potential of the batteries here. This is 3 volts, but I need to measure current. So I need to bring in a current meter. I have an electronic current meter which measures 0 to 10 amps. So I'll turn that on now to its 10 amp range. I'll prop that up so that the camera can see it. Okay, and I need to put the current meter in series with the battery supply. So I'm going to connect the meter through in series with the DC supply to the motor, and we now should be able to measure the current flowing during the running of the motor at 3 volts DC. And it's showing us that approximately 2.3 to 2.4 amps of current flows at 3 volts. So the product of those two will tell us that the motor is consuming approximately 7.5 watts of power in turning at that sort of speed. Now this motor is quite capable of being supplied with a much higher potential difference. Say for example 6 volts. I can supply 6 volts with this lantern battery, and we would expect the motor to develop considerably more torque with a 6 volt supply. Okay, so let's measure the power drawn by the motor at 6 volts DC. So again I have to connect my ammeter in series with that and connect the current, and you can see the current drawn now 3.3 amps at 6 volts DC. The product of those two, 3.3 times 6, will tell you it's about 20 watts now. So with 20 watts of power going into the motor, as you can see, it develops considerably more torque and more speed. In the reverse direction, let's see how much power is drawn by the motor in the reverse direction. I'll turn it counterclockwise. It was even more power, I think. Okay, so that's a quick demonstration of the operating principle of the 3-pole DC permanent magnet motor.